Hi there and welcome to Tutorial 6, which is an introduction to graphs and graph theory as it occurs in the EDEXCEL Decision 1 Maths module. Now, as always, this is applicable to most other Decision Maths modules at A-level. For any help with your other maths studies, GCSE or A-level, see my YouTube channel or my website below. Okay, let's start off with what EDEXCEL wants us to know about graphs. Now, here's the EDEXCEL specification, and it says that we've got to know various algorithms about graphs, okay, and how to represent graphs using matrices. Now, just to let you know, in this video, I'm going to be introducing you to what graphs are and the various definitions we need to know before we even move on to what these algorithms are. So we're not going to cover anything of this in this video. We're just going to get the basics covered about what graphs are, how to draw them, how to write them, and the various definitions we're required to know for the syllabus. Right, let's start off by talking about what a graph is, or what graph theory is. Well, what's graph theory? Graphs theory is the study of graphs to determine and model how objects are connected or related to each other. Now, if I was asking you what a graph was, to this point in your math studies, you might say something like that. It's something we draw on the xy axis, for example, the graph y equals x squared or y equals 9x squared. Now, for the purposes of this course, that's not what we're going to think of as graphs anymore, okay? We're going to think of something else as graphs, and a graph looks more like something like this. A collection of points, 1, 2, 3, 4, 5 points, that are connected to each other via these lines. And that is what we're going to talk about a graph means. Now, I want to spend the next few minutes actually showing you that you have been using graphs in the new definition throughout your life. You know about graphs already, you just probably didn't even realize that they were called graphs. So I want to show you various examples of these things you've been using in your life. The first one that we may use on a day in, day out basis, in particular if we live in London, is the tube map. That is a graph. Each of the stations are the points, and the tube lines are the connections between the various points. Okay, so we use a graph all the time to plan our journey. We may, for example, want to get from, say, Ealing Broadway over to Hammersmith, and we've got to plan out a journey between the two. Now, a problem that we might learn to solve in this module is how to get from one point on the tube map to another in the quickest possible distance. These are the type of things we're modelling. Now, an interesting thing, for any of you who might know, and I've done this journey quite a few times, okay, from Richmond, trying to get up to, say, maybe Ruislip up here, or Perivale. How do I get from Richmond to Perivale? Now, this has been a problem that has caused me a lot of grief. If you try and go up here, maybe try and get on the Piccadilly line, even though the Piccadilly line and the Central line seem to cross here, there's no station, there's no connection here, so it seems like you should be able to get from one to the other easily, but there's no connection. And this graph theory is all about how things are connected to each other, so that would be an interesting problem to solve, how to get from Richmond to Perivale in the quickest time. Right, let's have a look at another graph. On the theme of transportation, okay, the links between the airports in the world and the flights that go between them is a graph. Here is a graph showing the various different connections from different airports around the world. Something we use to get from different countries to each other. Okay, so another graph we use during travelling. Right, chemists also use graph notation, okay, and you may have seen this when you're learning chemistry. How chemicals or atoms are linked together, we usually use a graph to show how they're bonded. So here is a picture example of a graph, and here is a symbolic example of a graph, how those various chemicals are linked together, okay, or various elements are linked together. And there's another example of a graph we use in science. Computer technology is all about graphs in loads of different ways, but for example, a microchip is a set of connections between various little activities going on in these nodes here. So this is telling the computer how to do various things. It's a connection between all these various nodes. And a computer network itself, like the internet even, or a computer network in school, is a way of connecting computers between each other so you can communicate. So another example of networks and graphs that we use on an everyday basis. Right, another graph we use a lot, but we maybe even didn't realize it was a graph, is a family tree. The points on this family tree are the people in the family, and the lines between them show how they are connected to each other, through what relationship. So a family tree is another type of graph we use on a regular basis, and we may not even have realized we were using graphs. On the point of how people are connected to each other, a very important application of graphs nowadays is about social networking. How people are connected to each other using computers and social networking sites, for example Facebook, Twitter, Google+, LinkedIn, that connects people in the work arena. So the understanding of graphs and connections between people is a very big deal nowadays. And I'd like to show you a quick video that just summarizes graphs and social networking and how this is important to us in our everyday lives. So take a look at this video.
Networks get things done. Whether it's sending a letter or lighting your home, networks make it happen. To get from Chicago to Santa Fe, we need to see the network of roads that will get us there. We see that Chicago is connected to St. Louis, which is connected to Dallas, which is connected to Santa Fe. Of course, people networks can help us with finding jobs, meeting new friends, and finding partners. You know how it works. Bob is your friend, and he knows Sally, and Sally's friend Joe has a job for you. This is a network of people, a social network. Yay! The problem with social networks in the real world is that most of the connections between people are hidden. Your network may have huge potential, but it's only as valuable as the people and the connections that you can see. Boo! This problem is being solved by a type of website called a social networking site. These websites help you see connections that are hidden in the real world. Here's how it works. You sign up for a free account and fill out your profile. Then you look for people you know. When you find someone, you click a button that says Add as Friend. Once you do this, you and that person have a connection on the website that others can see. They are a member of your network, and you are a member of theirs. What's really cool is that you can see who your friends know and who your friends' friends know. You're no longer a stranger, so you can contact them more easily. This solves a real-world problem because your network has hidden opportunities. Social networking sites make these connections between people visible. Like a map for a highway, they show you the people network that can help you get to your next destination, whether it's a job, a new partner, or a great place to live. Your network is suddenly more useful. You can get started at these sites: LinkedIn, Facebook, and MySpace. I'm Lee Lefevre, and this has been Social Networking in Plain English on the Common Craft Show.
Okay, so thank you to that video from the Common Craft Show. It's interesting to see how graphs are working in everyday life. He used the word network there to say how we are connected to other people and how, by understanding those connections, we can actually make progress in our lives, for example, job opportunities, etc. So another way graphs are so important to us nowadays. Right, last look at a type of problem we're going to solve on this course. Imagine I zoom in on this part of the country and I'm thinking to myself, right, I'm taking my Aston Martin out for a drive and I'm going to start in Bedford. Okay, I usually do this on a Sunday afternoon. I love driving my Aston Martin, and I want to arrive at Cheshunt, okay, or Cheshunt. Now, the numbers between each of these towns or villages are, say, for example, the distances between them, or they could be the times it takes to get between them, or it could be the cost of petrol or something to that effect. The question I'm going to learn about in this course is how would I get from Bedford to Cheshunt in the shortest possible distance? And we're going to learn various algorithms to help us solve that. So an understanding of graphs and the algorithms that work on graphs is essential for everyday life. And you might be interested to know that our sat-navs and tom-toms and etc., they use these algorithms to program in how to get between various places. Okay, so understanding how these works is fundamental to everyday life. Right, let's go on to, at last, what the mathematical definition of a graph is. Okay, here is a picture of a graph. we have got points A, B, C, D and E and various connections between them. Right, there's a graph. Let's define mathematically what it is. The graph is a set of vertices or nodes and a set of edges or arcs that connect them. So, here's our picture of our graph. The vertices or nodes are these key points here. So I'll just label that in here. These are the vertices, and the other word for them is nodes. You need to know both words. They're used interchangeably in the exam. Okay, and it also says a set of edges or arcs that connect them. So for example, here is a connection between B and C. So this is what we call an edge or an arc. Again, you need to know the both words there. Now, that's a graph. All it is, a collection of vertices and nodes and a set of edges or arcs that connect them. Right, talk about something else. The order or valency of a vertex or node is the number of edges or arcs that are connected to it. Okay, so let's have a look at each of these in turn. If we look at A, there is 1, 2, 3, 4. Okay, 4 edges or arcs that are connected to it. So it has order 4. And similarly, all of them have order 4. If we go through it, we'll see that each of them have 4 edges or arcs connected to them. Now, one other thing you need to know, if the number of edges or arcs connected to it is an even number, this has even order. So even order, you need to know that. And say if that had 3 edges or arcs connected to it, it would be odd order. Right? So let's just formalize this very explicitly here. Vertices and nodes. What are they in this picture? Well, they are A, B, C, D and E. What are the orders of each? Well, the order of A is 4, B is 4, C is 4, D is 4 and E is 4. And lastly, how do we write the edges or arcs? Well, we write them by writing the 2 end vertices or nodes. So this one here I would call AE, this one here would call AC, this one here AD, and this one here AE, etc. So I need to go around the graph there and label them all in. So let's just check off I've done that correctly. AB, AC, AD, AE, and then we'd keep going through the ones we haven't done. So we'd have to do BC, which is next, BD, and then BE. And then lastly, let's go in a different colour pen, we'd have to do CD, and we'd have to do CE, and the very last thing we'd have to do DE, and hence they were the edges or arcs there. Okay, right, it's probably time you have a go at a few yourself, so pause the video and try and answer these quick, easy questions. Okay, what were the vertices or nodes? Well, they were A, B, C, D, E again. What were the orders of each of those? Well, A had 2 coming out of it, 2 arcs or 2 edges, so it was 2. B had 2, C had 2, and D and E just had 1. And what are the edges or arcs if we label them? Well, we had AB, BC, and AC, and we had DE. Okay, I encourage you to do one more question now, have a go at the next one, pause the video and I'll go through in a few seconds, just answering a very similar question to this, listing vertices, their orders and the edges. Okay, what are our vertices? Well, A, B, C, D and E again. Okay, A, B, C, D and E. What were the orders? 2 coming out of A, so 2. 1, this 1 coming out of B, this looped one, and 2, 3. So A was 2, B was 3, C was 2, E had 1, 2, 3, and 4, and D had just 2 coming out of it. Okay, so they were the orders, and the edges this time, well, we had an edge AB, we had another edge which was BB, another edge which was BC, then CE. Then we had 2 DEs, this one and 1 AE. So AB, BB, BC, CE, 2 EDs and 1 EA. It doesn't matter in this case which way around the letters are. For example, AE or EA. We'll talk about the ordering with a different type of graph later. Right, let's move on now. Hopefully that makes sense what vertices, nodes, orders, edges and arcs are and what a graph is. Right, let's take this another step further. Let's take a look at this picture. This was the last picture I dealt with there. There were a couple of things on here that require a definition. Namely, this peculiar thing here, okay, this arc or edge that came out of B and went back to B, didn't touch any other arc or edge, okay, and also these things here. There were two connections between E and D, so these are two things we need to know about. So let's define them. A loop is an edge or an arc that starts and finishes at the same vertex or node. This is therefore a loop. It starts and finishes at B. And the next thing we need to know about is what's called a multi-arc. A multi-arc is when two vertices or nodes are linked by more than one edge or arc. Here, D and E are linked by two, so this is called a multi-arc. These two combined would be a multi-arc. Okay? Right. Another definition we need to therefore know is what a simple graph is. A simple graph is a graph that does not have a loop and does not have any multi-arcs. Okay? So, let's take a look at a couple of pictures. This picture here is the one above. This is not a simple graph. Okay? I might even call this non-simple. Okay? Because it has both a loop and it has a multi-arc. Whereas this picture here, there are no loops there and there are no multi-arcs. So this here is what we define to be a simple graph. So I would call that one simple. Okay, nice and easy. So a few more definitions there. Okay, at this stage, I'm going to show you 10 questions. Okay, so on the next slide, I'm going to show you 10 multiple choice questions here. I suggest I will show you each of the questions. You pause the video at each one and just answer the question at the top of the page. Okay, so I'll show each one for 2 seconds, but you pause the video each time and make sure you can work through the answers. At the very end, I'll go back and just go through the answers. So question 1. Question 2. Question 3. Question 4. Question 5. Question 6. Question 7. Question 8. Question 9. Question 10. And now I'm going to go through the answers to these so you can mark your work. Okay, question 1. How many vertices or nodes? These are these things here. So there's 1, 2, 3, 4 and 5. Simple. The answer was 5 for that. Question 2. How many edges or arcs? There's 1 here, 2, 3, 4, 5, 6, 7 and 8. There are 8 there. Question 3. How many vertices or nodes? 1, 2, 3, 4 and 5. 5 again. Question 4. How many edges or arcs? 1, 2, 3, 4, 5, 6. 6. Question 5. What's the structure highlighted in red? Well, it's a connection between two nodes or vertices. So it's called an arc, but another name for it is also an edge. So you had to get B and C there. Question 6. What's that structure? Well, it's one of the points on a graph, and they're called nodes or vertices. So it's either a node or a vertex. Question 6. What's that structure there? Well, that structure there is a multiple arc or multi-arc, we called it previously. So probably multi-arc is what we called it previously. Okay, so two nodes or vertices connected by more than one arc, a multi-arc. Question 8. What's this whole structure called? Well, it's a graph, but actually it's not a simple graph because it's got loops and it's got multi-arcs, so it's a non-simple graph. What's this structure called here? Well, this structure here is a simple graph. It's a graph and it's got no loops and no multi-arcs. And question 9, what was finally this called? Well, this was a loop. It's an arc that starts and ends at the same point, so it's called a loop. Okay, hopefully now you've understood some of the basic definitions of graphs and the various elements of the graphs. Now let's press on with a couple more details on graphs and the other definitions we need to know. Right. Something quite interesting about graphs is called the handshaking lemma. Now, here are pictures of 4 graphs. Let's see if we can sort of work what this is out together. Now, remember the order of each vertex is how many arcs connect to it, right? So remember, we've seen this one before. Each of these had an order of 4 because 4 arcs were coming out of it. Now, let's work out the total order of this graph. The total order is therefore 5 lots of 4, which is 20. Now, the next thing to do, let's just out of interest count how many edges or arcs there are in the whole graph. So there's 1, 2, 3, 4, 5. 1, 2, 3, another 3, and 1, 2. So in total there's 10. So the number of arcs is 10. Right, let's move on and do the same thing over here. The order here is 2, the order here is 2, the order here is 2, the order here is 1, 2, 3, and we've done more. So the total order is 2 and 2 is 4, a 2 is 6, a 3 is 9, and this one, sorry, had order 1, so the total order here is 20. Now let's count up the arcs. There's 1, 2, 3, 4, and 5. So there were 5 arcs. Right, let's go ahead and do this one as well. Let's be careful here. This has 2. This C has 2. This E has 1, 2, 3, and 4. And this D has 2. Now we just need to be careful here with B. B has this one coming in and this one. And this loop will count as 2. So it will be 4. Because it's like 1 going out and 1 coming back in. So the total order is therefore 2 and 4 is 6, add 2 is 8, add 4 is 12, add 2 is 14. Okay, and let's count up the edges 1, 2, 3, 4, 5, 6, and 7. So the arcs or edges is 7. And let's do the last one here. We've got 2 here, 2 here, 2 here, 1 and 1. So the total order is 2 plus 2 plus 2 plus 2, which is 8. And counting up the edges here, we've got 1, 2, 3 and 4. So the arcs are 4. Now, this demonstrates the handshaking lemma to us. Maybe you can see what it is. If you look at this pattern, hopefully take a second just to see if you can work out what you think it is. And I'll tell you now, the handshaking lemma tells us that the sum of all the orders of the vertices or nodes of any graph is always equal to twice the number of edges or arcs. Okay, it's always equal to twice the number of edges or arcs. I'd like you, to pause the video and have a think about why that is. In 5 seconds I'll just have a talk through, but maybe you should pause and think to yourself, can you work out why that is? And the reason behind it, if you are adding up the order of each of the nodes of a graph, okay, effectively what you're doing is you're working out how many edges go into it, how many arcs go into it. And if you sum that up over the whole graph, that's your total order. However, that means you end up counting each edge twice because you go to each node and work out its order. So every time you end up counting up the arcs twice. So hence, by adding up all the orders, what you're also doing is you're also adding up each of the arcs, the number of arcs, twice. So hence, the sum of all the orders is always equal to twice the number of arcs. Okay, let's talk about something else really important about graphs, and this is going to be very important for our later work. It's called connection, how graphs are connected. Now let's take a look at these various graphs here. Now, what is connection all about? Well, the first thing I'm going to do is I'm going to tell you that two vertices or nodes are connected if there is a path or a series of edges between them. Okay? Now, let's say what I mean here. Let's say, is A connected with E? Well, yes. There's a way to get from A to E. Is A connected to C? Yes, because I can go directly. In fact, everything is connected to everything else in this graph directly. Now, is A connected to D? Well, not directly, no, but I can go via E to D. So they are connected, okay? Because I can go to E and then up to D. So there is a connection between A and D, okay? There's a path between them. And in fact, everything here can be connected. Can I get from C to A? Well, yes, I go here and here, or around here and around here. So they're connected. Right. Is, for example, B and E connected? Well, yes, I could go here and here, or I could go here and here. So yes, everything's connected up here. I can get from every place to another. Now, next thing, is A and D connected? Well, no, there is no way of me getting from A to D. There's no arcs that would connect to D. So A and D are not connected here. In fact, A, B or C, none of them are connected to either D or E. So that's what it means for a particular pair of vertices to be connected. Now, what do you think it means for a graph to be connected? Well, a graph G is connected if all of its vertices are connected directly or indirectly. Here, I can get from one vertex to every other easily, so it's connected. Same here. Same here. However, here, this is not a connected graph because D and E are only connected to each other. They're not connected to A, B or C. There's no way of getting between D and E and A, B and C. And that's what connection's all about. Now, just a point to just draw out here about connection. Although, let's say this arc here and this arc here cross over each other, there's no connection there. There is no node there, so there is no direct connection at that point. That's a bit like me trying to get up on the Piccadilly line and it crosses the Central, but I can't get between the two. So just to point out there, a key thing is there is no connection, even though the arcs cross over each other. Connections are only where there are vertices. Okay, let's move on to another element we need to know about graphs. Let's take a look at a very simple graph. Here is a graph with one vertex or node. It's connected because it's connected to itself. It is itself. Let's take the next most basic graph. Two of vertices or nodes, and they are connected to each other. There is a way from getting from A to B directly. Let's have a look at these 3 points here. They are connected. In fact, every point is connected to every other. A is connected to B and C, C is connected to B and A, and B is connected to A and C. So everything has a direct connection between them. I wonder if you can imagine what the next one's going to be I'll show you. Well, we're going to have 4 vertices here, and everything is connected to another one. A is connected to B directly, C directly, and D. B is to A, to B, to C, to D. C is to B, to A, to D. D is to C, to B, and to A. Everything is directly connected to every other node or vertex. Right, and the next one's going to have 5 points, and again, everything is connected here. Now, these are connected graphs. But more important than that, there's a special notation for them. They are called complete graphs because everything is directly connected to everything else. More precisely, every node is directly connected to every other node by an edge or an arc. So here's the definition we need. A complete graph is a graph where every vertex or node is connected to every other vertex or node directly by an edge or an arc. If a graph has n vertices, then the complete graph is called K subscript n. So let's just go back to our other graphs here and just write them down in their notation. This one here would be called, just going here, this one here would be called K1. This one here would be called K2. This one here would be called K3. This one here would be called K4. This one here would be called K5. Okay, so K5 there. Right, I'd like to pause the video at this stage and have a go at another question. It's a question about complete graphs. Okay, pause the video, have a go. There are 3 questions here, so I'm going to show you the first, then move to the second. You pause at each stage, try and have a go, then I'll go through the answers. It's important you have a go at these because there's some interesting points that come out and it's better if you attempt it yourself first. So here's the first 2 questions. In particular here, do have a go at question 2. Very interesting. See if you could work that out before I show the answer. And question 3. Okay, let's go through the answers to these. Going back to question 1. Draw K6. Well, it would have 6 vertices or nodes, and each one would be connected. I find the easiest way to draw these is like a hexagonal shape. There are 1, 2, 3, 4, 5, 6 there, and every one is connected to every other one. Okay, how many arcs or edges does it have, by the way? Well, that's just a counting exercise for you. And the answer is 15. Okay, just a simple counting. Go along and count up each of these, and you would get 15 when you do that. Now, how many arcs or edges would Kn have for any number n, and why? This is a very interesting question. I hope you attempted this, but a nice way of showing it is to talk about what happens in each of the other cases. Now, K1, how many arcs or edges? It had none. What about K2? It had 1. What about K3, if you remember? It had 2. K3 was like this. 1, 2, 3 even. Sorry, it was 3 there. It had 3 connections between it. What about K4? If you remember, K4 was like this. It had 1, 2, 3, 4, 5 and 6. And K5, it was like this. So it had 1, 2, 3, 4, 5, then it had 6 and 7, then it had 8 and 9, and I'm missing one here, it had 10. So it had 10 there, and we're saying K6 has 15. Okay, I wonder if you can spot the pattern between the number here, 1, 2, 3, 4, 5 and 6, and the answer you get at the end. That's the question there. Or can you work out a reason why it might be the case? Well, the answer for Kn actually turns out to be n multiplied by n minus 1, all divided by 2. Now, why on earth would that be the case? Where has that come from? Well, that's a formula linking the n here to the answer here. Okay, because 1 times 0 over 2 is 0, 2 times 1 over 2 is 1, 3 times 2 over 2 is 3, 4 times 3 over 2 is 6, 5 times 4 over 2 is 10, and 6 times 5 over 2 is 15. So it works. But why does it work? And what's the rationale behind it? Well, I say the easiest way of talking about it is as follows. Just take a vertex in isolation, okay? If you were to work out, okay, how many edges came out of that one, if it was a complete graph. So say if it had, there was n nodes in the graph, then to connect from this point to every other one would be n minus 1 arcs, okay? So in this case, because there are 6 here, you need 1, 2, 3, 4 and 5 to connect to all the other nodes. So there are n minus 1 arcs needed. Right, now imagine doing that for each of these. Okay, if you did it for A, B, C, D, E and F, you did it for everyone, you would have to do it for however many there are. Okay, so in this case there are 1, 2, 3, 4, 5, 6, but in general there are n of them, so you multiply it by n. That would tell you how many arcs there are, but the only problem is you've counted everyone twice, okay? Because if you then go to B and count that one, that one, that one, that one, and that one, you've counted this one twice. And going through all of them, you end up counting everyone twice. So it's n minus 1 times n, and then divided by 2. Or I might write that as n minus 1 over 2, just neat to algebra. And that's the sort of rationale behind that there. The next question, which of these graphs were complete? Well, this certainly isn't complete, okay, because these two aren't connected. Okay, this certainly isn't complete because it's not even a connected graph. This is complete. We've called that K3 before, okay? And what about the other ones? Is there a direct connection between each of these? Well, this one here, there's not a direct connection between, say, there and there, so this can't be. But here, everything is connected up, so this is another example of a complete graph. Right, let's continue with something else we need to learn about graphs. Okay, so going back to our original graph, that was our definition of a graph, and I'm going to use that to draw out some new definitions, okay? So looking at that graph, let's change something and talk about what this is. What I've changed here is I've assigned numbers to each of the edges or arcs. Now these numbers could mean the cost of getting from A to B, or the length of wire to get from A to B, or the time it takes to get from A to B, etc. So these are called weights here. When you assign numbers, that's called weight. Okay. Now all a network is a weighted graph. It's a graph and it has weights assigned to it. Okay. So in this case here, the weight of AB, let's say, is 7. The weight of AC is 11. The weight of AD is 20. The weight of AE is 5. The weight of BC is 15. And keep on going. The weight of BD, I think that's 15 as well. BE would be 3. CD would be 6. CE would be 12. And lastly, DE, D to E would be 14. Okay? And they're the weights of that graph there. Right, let's take a look again at our original graph again. There's our original graph. Let's change something about it and draw out a new definition. There's a graph. Here's a picture of a very similar graph, but it has directions associated with it. To get from A to between A and B, you have to go in that direction. That's what that arrow means, okay? And this is called a digraph. A digraph is a graph where the arcs have a direction associated with them. Okay, so it's very important when we label out our arcs or edges here, what they are. I can't write BA, okay, is the arc or edge. It's not. It's from A to B, right? So if I was you, I'd pause the video and just see if you can correctly label what the arcs or edges would be. I'll just draw in these arrows to make it a bit clearer. That was the direction of that one. That was of that one. That was of that one. This one's going this way. This one's going that way. That one's going that way. This one's going that way. That one's going that way. So just take a second, pause the video and label in the arcs or edges in this case. Okay, so here are the answers. A to B was one, okay. A to C was another. D to A this time. You had to get it that way right. It's important. You can't go A to D. You go D to A and A to E, then C to B, D to B, and E to B, and C to D, C to E, and E to D lastly. Okay, so it's important how you label your graphs up there. Right, next thing we need to talk about, let's move on, is an isomorphic graph. Isomorphic graphs are graphs that show the same information but are drawn differently. And by that I mean they have the same number of vertices or nodes and the arcs and edges, and the connections are identical. So really, it's a question, if I wanted to draw an isomorphic graph to this, it would have the same number of nodes, the same number of edges, and the connections would all be identical. So here's one I've drawn here. You see all the connections are the same. I've got A connected with B, B with C, C with D, and D with E, but I've also got that AE connection in there. Okay, so I've just drawn it in a different way. And here's another picture just like that. A and E are connected, D and E, C and D, C and B, and A and B. Those graphs, those three graphs are called isomorphic. Right, keeping on going. That's our original definition of a graph again. There's our original graph. And I want to draw out some new meanings here. We're nearly there now. A subgraph of a graph G is a subset or part of the original graph. So if this was our original graph here, all I've done here is taken out a few arcs or edges, and it's a subgraph. Okay, it's a part of that graph. Okay, it doesn't have that connection, that one, or the other ones, but it's got all the vertices in this case and some of the edges missing. And here's another example here of a subgraph. Okay, it's part of the original graph but doesn't have all the connections in. Okay, nice and easy. Now, the next thing we need to talk about is a path. What's a path? A path is a sequence of edges or arcs where the end vertex of one edge or arc is the start of another, and no vertex is visited more than once. Okay, so imagine this is our original graph. I'm going to show you an example of a path. A path is here. If you take a vertex there and you join it to there. Now, the end, the end vertex of this line here is B, but it's the start of another line here. Now this is an example of a path. Okay, a path, I can draw a path from A to E without taking my pen off the page and without going over the same vertex twice. And at any point, okay, let's say at that point there, okay, that is the end vertex of the line BC, but it's also the start vertex of the line or arc DC. So that's an example of a path. Okay, and here's an example of another path. Let's go from A to B to E to D and to C. There's another path for us there. And at any point here, this is the end vertex of the arc BE, but it's the start vertex of the arc ED. Now, how we would write a path down, we write a path very clearly. We would call this the path A to B to C to D to E, and we would call this the path again A to B, this time to E to D and to C. That's how we would write our paths. And the key thing here is no vertex is visited more than once. Okay, let's talk about when a vertex is visited more than once. Okay, a walk is a path where you can revisit a vertex. Okay, you can still trace the thing without taking your pen off the page, but you end up repeating vertices. Right, let's have a go at drawing out a walk. Right, here is an example of a walk. Okay, I've gone from A to B to E to D to C and back to D, and that's a walk, okay? I have revisited B a few times, so I've gone A to B, here to here to here to here, and back to there. So I revisited B and D twice there, okay? So that's an example of a walk, and let's do another one over here. Let's take a walk from E, go from E to D to C and back to B. I ended up going back to B twice, and the walk here was E to B to D to C and to B. So I could trace it without taking my pen off the page, but I ended up visiting or revisiting a vertex more than once. Okay, next thing. What's a cycle or a circuit? Where a cycle or a circuit is a closed path. It's one where the start vertex is the same as the end vertex. So let's draw an example here. A to B to C to D to E and to A. You started at A and you ended at A. So a cycle here would be A, B, C, D, E and A. You start and end at the same vertex. So that's a cycle. And let's draw another one here. Let's go A to B to E to D and back to A. You started and you ended here. So we went A to B to E to D and to A. And that's another example of a cycle or circuit. So it's a closed path where the first and last one are the same. Okay, we're nearly there now. We've only got a couple more things to talk about and we're done. We need to discuss what a tree is. Now, a tree is a connected graph that has no cycles in it. You cannot find a cycle in a tree. So, for example, let's show you what a tree is. Although this is connected, okay, definitely connected. I can get from anywhere to anywhere else in that graph. It's a cycle. There is a cycle in it. A, B, C, D, E, A. Or E, A, B, C, E, D, E. There is a cycle in it, okay? So that's not connected. But by, let's say, deleting one of these, then I'm certainly connected, because although I'm not directly connected from A and E, I can get along here to E, and there is no cycles at all in there. So that's an example of a tree, okay? So let me draw you another example of a tree in this one here. Why don't I say, for example, I'm going to connect from there to there, there to there, there to there, and there to there. Now everything is certainly connected. There's a way from getting from every vertex to another one, but there's certainly no loops there. So that's another example of a tree. Let's draw what's not a tree here. There to there, there to there, and there to there is certainly connected, a connected graph, but there's a cycle. But by deleting any one of these, it makes it a tree, because I've still got the connections I need, but there's no cycle. And let's straight away, I'd probably suggest you pause the video here, see if you can have a go at drawing a tree with these four here. And I'll go through in 2 seconds. Right, let me draw one for you here, and let me just see what you think. Do you think that is a tree? Well, that's not a tree because it's not connected. I can't get, for example, from D to E because there's no vertex here. So that certainly isn't a tree. I was tricking you there. Okay, what about this one? Is that a tree? Well, it's certainly connected. I can get between all of them. However, EB and EBCE forms a cycle, so that's not a tree. Okay, so no good. Okay, about time I stopped messing about and actually draw a tree. An example of a tree here would be something like this. Everything's connected, but there's no cycles, so that's an example of an easy tree there. Okay, and the last thing we need to talk about is spanning trees, okay? So, a spanning tree of a graph G is a subgraph of G and a tree, is a subgraph of G and it's a tree, and it connects all the vertices, okay? So it it makes a connected tree so that all the vertices are connected. So here's our original graph G, and a spanning tree of that is a subgraph of this where all the vertices end up being connected. Okay, so let's have a go at drawing one. For example, this is a spanning tree. Everything is connected, okay? Everything's connected. I can get from any one to any other one via A, but there is no circuits or cycles, so it's a tree and everything's connected. So there's an example of one. Let's have a go at another example of one here. I could, for example, do something like this. And again, everything is connected there. Okay, everything is connected, but there are no cycles. So this is an example of a spanning tree, something that connects all the vertices, okay, and is a subgraph of the original graph. Okay, now you'll notice here that this graph, okay, had 1, 2, 3, 4, 5, 6 vertices. That was the original graph. The spanning tree had 1, 2, 3, sorry, it was 5 here. This was 5. And the spanning tree had 4 arcs, and this spanning tree had 4 arcs. Okay, and in general, for any graph G with n vertices, any spanning tree has n minus 1 edges or arcs. Okay, that's just because if it had n, you would certainly have created a cycle or a loop, a cycle or a loop, yeah, so you would not have a tree. And there we go. That's pretty much everything you need to know on the definitions of graphs for this course. Now, I've just got on the next slide a set of questions for you. I just encourage you to pause the video, have a go through these, okay, and then I'll go through the answers. So pause the video here, work through these. Right, let's go through these. Which of these are complete? What does complete mean? Everything is directly, or every node even, is directly connected to every other node, okay? So, right, this is, S certainly is, okay? No, it's not even, let's just cross off what can't be. No, there's no connection there, so that can't be the case. No, there's no connection there, so that can't be the case. Yes, that is. No, these aren't even connected. Okay, no, that's not connected to say there. What about here? No, because that's not connected to say there directly. What about here? Well, no, that's not connected to there, so no. No, certainly not, that's not connected to there, and no, that's not connected to there. This is, so S and P end up being complete. Okay, and remember what we mean by complete. Every vertex is connected to every other one. Okay, which ones are trees in this case? Tree, remember, has no cycles. That has a cycle there, no good. That has a cycle here, no good. This doesn't have a cycle, so it's a tree, and everything is connected. This has a cycle, so no good. Okay, this is no, because everything's not connected here. Okay, we're not fully connected up, so that's not a tree. This is, everything's connected up and there are no cycles. Now remember, that looks like a cycle, but there's no connection there, so U is certainly a tree. Is this? Well, no, there are cycles here, for example, there. Cycles here, for example, here. No cycles here, so this looks like it is a tree. And again, no cycles here. This looks like it's a tree. Everything's connected up. Okay, which ones are simple? Remember what simple meant. It meant a graph, okay, that had no loops or multi-arcs. Okay, now let's have a look. No loops or multi-arcs. Let's cross out. There's a loop. There's some multi-arcs. And that's it, as far as I see. So all the rest, actually here, this is connected to this one here, and it's connected there. So that effectively is a multi-arc. So everything except Q, T and V. So that would be P, R, S, U, W, X and Y. And lastly, digraphs. Let's remember what a digraph was. A digraph was a graph that had some direction associated with it. You had to go along a certain direction. Now here, there's a direction there, here there's a direction, so these two are the only digraphs, so W and X. And hopefully you were able to answer those questions. Okay, just to finish with then, just wanted to show you some of the definitions that are given to you in the D1 glossary, and all of these you're expected to know and quote, and at this stage, apart from maybe this one here, okay, we've gone through everything in this section, but we're going to do this later on. So I would make sure you've got a copy of this and know all those definitions. Finally, just for homework and further study, I would suggest you go through the entire of chapter 2, pages 25 to 33 and 38 and 39, and work through the examples in the book. Then do exercise 2A, questions 1 to 6, and 2B, 1, 2, 3 and 5. Last thing I suggest you do is you go to my past paper questions 6 video, where I do the exam questions that have come up on these definitions of graphs. So that would be a good way to test you actually do know your definitions and could answer exam questions on them. Thank you for watching this video. I hope you found it useful in your study of D1 graphs and your revision. Thank you for watching, and please tune in for your next video.